All right. So here is my presentation, what I could potentially be using for a back-to-school night in the future, or a video to be sent home, maybe via email before back-to-school night, just to get on the same page with parents about what they are to expect for the upcoming year, and why I make some of those choices. Okay. So our first goal this year is to create motivated learners. That's the main thing that we have to be aiming for, especially in this math class. So the real idea here is that I'm going to attempt to take down the barriers to motivation. It's my belief that every student has motivation within them, but sometimes we set it up in school so that we take away those things that naturally motivate them. So there's been a lot of research on this. Brophy writes about this in his book, Motivating Learners. So the three parts to real motivation are autonomy, competence, and belonging. The desire for autonomy, the desire for competence, and the desire for belonging. So first, that autonomy part. Students want to be in control of their own learning. People want to be in control of their own lives. So this is going to drive motivation. If they're in control, they're going to be motivated to do more work. If I tell them, hey, you're doing A, B, and C, and you're going to do it my way or the highway, that takes away motivation because they don't have that autonomy. Second is the desire to be competent, the desire to be good at something. Now, I think where I come in play here is I have to give them things, give them tasks, and give them activities that are worth being good at. If we do 50 long division problems, most of our students are not going to be motivated, to be good at doing 50 long division problems. They're not going to care all that much to be competent at it. So my job is to give them interesting tasks and then put them in positions where they want to be good at the thing that they're doing. And finally, motivation. Part of motivation is feeling that they're part of the group. So when students are either falling behind or they're not doing things that they're interested in, they don't feel like part of the group. So if I can reverse that and I can use that sense of belonging to increase motivation, like, hey, we're all gonna work on this same type of problem. You're part of the group. We need your input. That is all going to increase motivation. So ways that I can take away motivation is by telling the students exactly what they have to do and when they have to do it, giving them problems they don't care about being good at, and isolating them from the group. So those are the barriers that I find are typically up in schools. So I want to take away those barriers so that their natural motivation can show. All right, so what are we going to be doing in this class? Something that I've discovered over the last couple of years, and has been backed up by research and authors in the field, is that math does not have to be painful. If math is miserable, we're setting it up the wrong way. So if my students don't want to do a problem, that's it's my fault, or the way I've set up the class is incorrect, because it's not driving them to enjoy what they're doing. So how are we going to do that? We're going to use problems that are accessible to all students but provide a challenge at higher levels. So Jo Boaler writes about this. She calls it the low floor, high ceiling, which means that every student can get their hands dirty with a problem, but it can be solved at really high levels. And I'm going to have some examples of that later on. But this means that we are not going to see a whole lot of problems where it's one sentence. Mary went to the store. She bought 5 apples. Each apple was $1.69. How much money did she spend? That could be above accessibility for some students, and that can't be solved at a high level. It's not a very provocative question. Next, we're going to use problems as puzzles, and Jo Boaler writes about this too. in terms of what motivates students to really get into something. If the problem is a puzzle, it's something that the students feel like they have ownership of. If you think about an actual puzzle, the way you solve an actual puzzle, you take a piece, you try to put it in a spot, oh, it doesn't work, oh, let me see if it fits somewhere else, it doesn't work, let me see if it fits somewhere else. The actions are determined by the student. They're free to try out different things, and they're trying to unlock, they're trying to unlock this kind of answer. So we're going to be doing problems that motivate students to dive deep into them. Similar to that, students are going to be using their own ideas in a problem. Again, I have some few examples of this in the future, coming up in future slides. But when the students can use their own ideas, again, it gives them that sense of autonomy. It gives them the sense that what they do matters. They aren't trying to, like I don't have a problem that's set up where the answer is 7 apples. Oh, Mr. Z has the answer. He's got the answer. Let me just try to figure out what he's thinking. No, when they can use their own ideas, they can attack a problem from different angles and come up with their own thing. And lastly, students can interact with the problems. This might mean that we're using manipulatives. We're using base 10 blocks, where, hey, maybe you forget how to carry. What does it even mean? You forget how to regroup. Well, again, what does that even mean? If they can interact with the problem, they can take out some base 10 blocks, and they can take, 10, a big 10 cube, and they can slice that thing up into 10 different pieces. They can physically interact with the problem. Also, maybe they can actually go and search out information on their own. They can fold up a piece of paper in a certain way. They can use counters in a certain way. They can actually interact with the problem on their own. And again, a lot of these ideas, these types of problems come from Joe Bowler in her Mathematical Mindsets book. And there are a lot of them are great strategies for having students be interested to solve problems. Okay, so my guiding philosophy when I'm setting up these problems and when I'm making lesson plans is that students remember what they think about. Now that was found in an article by Daniel Willingham, a cognitive scientist, and the idea here is that it's kind of on repeat of what I've been saying, is that if a problem matters to the students, they're going to think about ways that they can solve the problem and ways that they can overcome obstacles. That's what they're thinking about. If I give them 15 long division problems, most of them are going to be thinking about, this is so boring, I can't wait till it's done, I don't like math. Okay, so now 6 months down the road, what are the students going to remember about that long division experience? They're going to remember what they were thinking about. They were thinking, oh my gosh, this is so boring, I can't wait until we can just get out to recess, I can't wait until we can get to lunch. I need to give them activities where they're thinking about the math. If they're manipulating base 10 blocks and they have a 10th and they're trying to cut it up into pieces to maybe do some regrouping, they're thinking about, how can I take this solid 10th and break it into its pieces? So then when they go back and remember that, they say, oh, that's all right. I remember I had this mental picture of that, of taking a long and breaking it up into cubes. So that is a huge part of how we're going to attack our problems, is putting our students in a position to really engage with the problem, think about the problem, because that's the thing that they are going to be remembering. All right. So here's some examples of things we were talking about. So we'll set them up with the problem. I'll set them up with the Fibonacci sequence. I'll give them the first couple of items, and then their job is to figure out the rule, and then to fill in the 3 remaining pieces there. So this is an open-ended problem. It's a puzzle problem. They can try to solve it by, figuring out what are the differences between each number. They can use a calculator. They can graph things. They can take some blocks out and see if they can find any patterns. There are many, many ways to go about solving this type of problem. Now, what I would start the lesson off with is by saying that this famous sequence controls or describes the way that a wave curls in on itself and it also describes the way that a galaxy spirals in on itself. So there's some real interest in there, and that in and of itself is amazing. There's a lot of other examples like that. But when we set up this problem this way, it's like, wow, okay, math matters, math is real, math is interesting, math is amazing. What the heck does a wave have to do with a spiral galaxy, and what does that have to do with the seashell? So we're giving our students the ability to be flexible problem solvers, and we're giving them a problem that they care to be good at. If it's an interesting natural phenomenon, they're going to care to try to solve it. So another example then that we use on top of that is Pascal's triangle. So they'll be given something like this, again, where we have the beginnings of a pattern, and then they have to fill in the blank spots. They can go about this 1,000,001 different ways. What do all of the columns have in common? What do the rows have in common? What can you add up between things? What can you subtract between things? There's 1,000,000 different ways you can go about it. And that's exactly what we want. We want students to realize that math is something to be figured out. It's not something necessarily to just simply be memorized and, hammered away, and did you remember it or did you not remember it? There's a small portion where maybe that plays a role, but that's not the real essence of what we're showing them. So this type of problem can really drive that increased interest in what we're actually doing. Going, to the Daniel Willingham paper, The Cognitive Scientist, if they're really attacking this pattern, they're thinking about, okay, are we adding, are we subtracting, are we building things, are we breaking things? They're thinking about the problem solving, therefore they're going to remember the problem solving. Now, here's the kicker. After we do those two activities, what we do is we show them when you add up the diagonals of Pascal's triangle, when we sum up the diagonals, the sum is the Fibonacci sequence, which is just, it's ridiculous. It's unbelievable. And if we spend a good amount of time really talking about Fibonacci and really talking about Pascal, and I show them as completely separate things, when I show them this slide, or when we actually do it and they find Fibonacci within Pascal, it's just unbelievable. And they're in awe of what math really can be. And it's not always that way. It's not always, amazingly interesting, but it can be. And that's a huge part of what we want to show them, is that it can be amazingly interesting. It can be something that you want to be good at. That's that competence. It can be something where you have the ability to solve a problem the way you want. That's autonomy. It can be something when you work with a partner, you guys come up with this thing together. And when you do something together, it's a great feeling, and that's that belonging. So we're hitting those three big key pieces of motivation. So that's amazing. Here's another type of problem we've done. It's a Dorney Park problem. It says, I've talked about this in some of my discussions, but it's a problem where the students actually have to go and research how much a ticket costs. They have to count how many people are in the room. They have to come up with a price. And again, this is, hey, where are you going to go on the website to figure this out? Are you going to include the teachers in these tickets? This $12.87 per hour, it does not come out to be exactly the amount that we need for Dorney Park, when you multiply it by the hours. So some students say, hey, you have to work for a week because 4 days isn't enough. There's multiple answers. The students can attack it from multiple ways. And then when they have to do the multiplication matters. When they have to do the division matters because they're invested in the problem. Okay, so in conclusion, I want our students to be experiencing math beyond the calculator. Some students view using the calculator as cheating, but with the math that we are going to do, that reliance on a calculator it doesn't matter as much because it's not the critical element in these interesting puzzles that we're doing. It's more than simple calculation. Students will find that they have the answers. So just like with the Dorney Park problem, there's multiple answers to that problem depending on what you counted. You have the answer. Now prove to me that that's right. The Fibonacci sequence, there's a couple different ways you can figure that thing out. You have the answer. Now prove to me that it's right. Pascal, same thing. There's one set, final way that it should look, but there's different ways to get there, and there's different reasonings behind it. So if you have the answer, again, tell me how it makes sense. And hopefully, what we'll end up with is that we're going to lose that fear of